All right, the Chapter 10 review for exam number 2. This is the third and final chapter that we will be covering in this exam. So let's go through the topic list. Okay, so Chapter 10 starts the operating systems layer, which is the portion of a computing system that enables it to be a little more usable for and by lay users. So basically anybody who's not a computer hardware systems programming expert can now use modern computers because of the operating system, because it provides this level playing field for us to interface with the computer. And we don't need to be those low level programming experts. We can just utilize the system as a whole. So the role of the operating system is to manage the interactions between the application software and the system software. It provides management capabilities for the computer resources, such as memory and input-output, and provides the interface through which a human can interact. So different hardware components, the actual power up, power down processes, things like that. Let's see, the difference between system and application software. System software being the programs that allow the computer to function at a very low level, so that the different hardware components can interact, so that the different memory management processes are completed, things like that. And then the application software is whatever we as human users choose to install on the machine for our personal use. So office programs, media streaming programs, anything that we would use as human users. The difference between a program and a process. A program is the actual code that is stored in memory, and the process is the dynamic entity that actually exists during execution. So the process itself has a lot of extra information that the system tracks about it to make sure that it executes correctly and executes completely. So multi-programming. This should be familiar from your homework. Multi-programming is the ability of today's modern systems to keep multiple programs in memory. It may sound kind of simple, but there were days when a given machine could only hold one program at a time. So this is a very typical feature for today's computers to have. And it is made possible through process management and memory management, because we need to be able to keep track of where things are stored, as well as to manage the different processes trying to share these resources all at the same time. So let's see, memory management and process management. Let's see. Oh, time sharing. So there are many systems today where multiple users are trying to use the same system at the same time. This is particularly present in the industry. If you've ever worked in retail or food service or anything like that, where you are interacting with a point of sale system, typically you as the cashier will stand at a terminal and enter the information about the transaction. And typically the terminal itself is not a standalone computer. It's actually talking to a system like in the manager's office or something like that, and performing operations on your behalf on that primary computer. So the concept of what's called a dumb terminal is basically like my computer is giving me the impression that I have a standalone system by itself, but in reality it's just farming those operations back to the primary computer. So memory management, let's talk about that. In memory management, the whole goal is to be able to store all of these different programs effectively and efficiently, so that there is a minimum of wasted space. When space is at a premium, it's your number one commodity for memory management. But it is impossible for a program, when it is written, to know where it is going to be stored. So if I need to retrieve my next instruction, I can't know exactly where in memory my next instruction will be. Therefore, we have what's called a logical address. A logical address is just some sort of pretend address that we reference. We don't really know where we're going to be stored, but I'll just pretend that it's address 16 for now. And then the actual physical address, where that instruction is in memory for real, will then be swapped out for the logical address at runtime. And the process of doing that conversion is called address binding or translation. So there are a couple different memory management techniques that the book discusses. Single continuous memory management is just the memory is just treated as one solid block, and you put in one program at a time, and that's it. And it's not very efficient because the whole idea is to have multiple programs in memory. So if you can only have one, that's not ideal. That's not fun. Partition memory management is the next step. So divvying up your memory into different chunks. You can do either fixed partitions, which are these are the partitions and they always stay the same, and you can never change it once the system has booted up. There's also dynamic partitions, which is the opposite of fixed partitions, where you can change them as time goes on, but then you need to make sure that address binding is performed appropriately. Now, when it comes time to do your address binding or your address translation from logical to physical addresses, you have what are called your base register and your bounds register, which says for this program, for where it's stored in memory, it starts here at the base, and that starting point is stored in the base register, and it goes this far. And that's that limit is stored in the bounds register. And then based on those two values, you're able to do your address translation. So if I know that my program is looking for address 16, then I simply take the base register and add 16 to it, and then that's where I go for my next instruction. So how do you work with these partitions to pick a partition to put your program in? There is first fit, best fit, and worst fit. First fit means start at the top, go to the bottom. As soon as you find one that is big enough for your program, plop it in there, call it good. Unfortunately, you can end up with a lot of wasted space that way, so it's typically not considered to be the best option. Best fit gives you the smallest partition of all available partitions that is still big enough to fit your program. Now, it's possible and highly likely that you will end up with a very, very small amount of memory left that is probably too small to be usable after that, which is where worst fit comes in. If you put the program in the biggest partition that is big enough to fit your program, then you maximize the likelihood of having a chunk of usable memory left over that can still fit something useful. Let's see. And then the third option is called paged memory management, which breaks up your memory into fixed chunks, and then your program is split out into however many chunks it needs to cover all of the memory requirements for your program. This does require considerably more manipulation on the side of the management system, because now you need to keep track of, for every program, what pages it's taking up, where they are, the order that they should go in. So it makes your address translation, your retrieval process, all of that, a lot more involved. So let's see. So the memory is divided into chunks called frames, and then the corresponding chunks of the process, the loaded program that fit into the frames are called pages. So know the difference. Frames are the chunks in memory that are carved out. Pages are the chunk of the process that go into the frame. And then you have to keep a separate table that maps the pages to the frames. So the chunk of the program to the chunk of memory where it's stored. And then they can be swapped out as needed. If a process finishes and you don't need its program instructions anymore, then you can dump them from memory and perform a swap, bring in new pages. Unfortunately, if your memory, your primary memory where you're storing these pages and is too small, and then you have to swap out pages very frequently, then you can end up in what's called a thrashing situation, which is you're swapping things out way too quickly. You can't actually get anything done, and the system just sort of freaks out. So process management then is the logic of dealing with these programs as they're executing. So remember, a process is the actual dynamic entity that represents a program as it's being executed. So a process can have a number of different states. If it's new, that means we just loaded it. It's ready. It's being added to. It's been created and added to the queue. When it's actually ready to be executed, has all of its initialization needs met, then you move to the ready state. So it goes from new to ready. And then from ready, you can then start running when it's your turn to use the CPU. And from running, you're either waiting, which means that you have encountered some sort of stopping point. You need either some sort of input-output, or you're waiting for a particularly involved event or something like that. And then once you've received your information, then you move from waiting back to ready. Or you could also be interrupted from the CPU and kicked back to ready. So you go from new to ready, and from ready to running. From running, you can either go to waiting and then back to ready, or you can go to back to ready and then running again whenever you get your turn on the CPU. Once you've completely finished your execution, you're all done, then you move to terminated. The process control block is a data structure that just stores all of the information about the process, any sort of context-based information that would be necessary to kick execution back up when the process gets control of the CPU again. All sorts of different data points in there that the system needs to track. The actual exchanging of information when one process stops using the CPU and another one starts up is called a context switch. There are a number of different ways that you can schedule which process gets to use the CPU at a given time. There are two categories of scheduling, either preemptive or non-preemptive. Non-preemptive means that the only way that a process can be removed from the CPU is if it voluntarily gives up control. That's non-preemptive. Preemptive means that we can interrupt a process running on the CPU whenever we want. First come, first served is first on the list of CPU scheduling algorithms. It is a non-preemptive approach, and it basically just says whatever algorithm or whatever process gets there first, it runs until it's done, and then we move on to the next one, and it runs until it's done, and then we move on to the next one. It is considered to be more fair, but it's not very efficient because the turnaround time for processes tends to be very long. They tend to wait a really long time before they get to the CPU. Shortest job next is also a non-preemptive scheduling method, which says we're going to schedule these algorithms, or we're going to keep saying algorithms. We're going to schedule these processes based on how long we think they're going to take. And typically this would be considered the best option, because you would give those processes that are going to get in and get out, you would give them priority. But we can never know for sure which processes are going to finish the most quickly. So this one typically isn't used very often. Round robin, however, is typically used. It is a preemptive scheduling method, which says we do interrupt a process when it's on using the CPU. So each process is given what's called a time slice. So it's given a certain amount of time to use the CPU, and when it's done, it is kicked out and it goes back into the ready state. And so each process gets a certain amount of time, and we just continue through this cycle until all of the processes have finished. And it's generally considered, at least out of the ones that the chapter addresses, this solution is generally considered to be the most fair. I think that's it for chapter 3, or sorry, these 3 chapters, this one being chapter 10. So yeah, if you have any questions, if there's anything that I didn't cover that you wish I had covered, shoot me an email, and I will get back to you. So good luck, happy holiday, and I'll talk to you later.